Good evening, sir.
Yes, ma'am. Good evening.
You can start,
Good evening,
sir.
sir.
Yes, ma'am. Who is this talking?
Sir, yes, sir.
What, you are not regular to the class?
Sir,
Why you weren't regular to the class? Last class, where were you?
sir, last class I had a function in school, sir.
I'm also having everyday function. I'm attending the class regularly. No, I'm taking class. No. Huh?
Sir, it was compulsory to attend, sir. Full day I had to be.
Oh, this is not compulsory. Huh? Where's that? No response from your side. Hello.
Sir, no, sir. The school said that I had to attend, sir. There was no choice
Huh?
to do.
Huh?
Sir, no choice given to me, sir.
What's given
Every,
to you? No choice given to you.
yes, sir. Everyone in 11th and 12th were given duty, sir.
Okay. Ma'am, are the other students joining?
Sir, you start, sir. They will join, sir.
Okay, because they again have to repeat, no, when they come. That's the problem. That's why I'm asking.
No need, sir. You continue.
Okay, madam. So we'll continue. Ajay, last class's video you just see. All right.
Yes, sir.
We learned an important theory. That's called as Werner's theory. All right. We learned Werner's theory. So I want you to go through that postulates of Werner's theory.
Yes,
There
sir.
are 5 postulates, and I was supposed to discuss some other topics based on Werner's theory. We will learn about that a little later, but we'll go for the next theory. Werner's theory for coordination compounds will finish. The next what we have is called as valence bond theory. Based on this valence bond theory only, we will be in a position to predict the structure or the geometry of the complex. The structure or the geometry of the coordination compound will be based on valence bond theory. So postulates of valence bond theory. Firstly, we should learn the postulates of valence bond theory. What are the postulates of valence bond theory? There are 6 to 7 postulates which we have to learn. All right. So here they've not given in detail. It's not typed in detail. We will learn. I'll teach you. I'll just check where there's a place. Yeah, there's no place here. Yeah, here. Now, postulates of valence bond theory. Valence bond theory is abbreviated as VBT, valence bond theory. So predicting the structure of certain complexes based on valence bond theory. All right. Now, what is the first postulate? There are 6, 7 points I told you. Now, the first point here is the central metal atom. Central metal atom or ion produces or furnishes definite number of vacant orbitals. Vacant orbital. What's the first point? The central metal atom or ion produces definite number of vacant orbital. This is the first postulate in valence bond theory. Now, what do you mean by central metal atom? If I write a complex like this, where is that? Oh, 1 minute. If I write a complex, if I write a complex, 1 minute, this my writing pad is giving some disturbance. It's not having some loose contact somewhere. So the central metal atom, if I write a complex like this, if I write a complex like this, Cu, something wrong, man. So far, so good. So if I write a number of vacant orbitals, now if I write a complex like this, Cu, NH3, 4 times SO4, If this is a complex, the central metal atom or ion is copper here. In this case, it is copper. Whatever is in the square bracket is called as complex ion. So in the complex ion, the metal present is called as a central metal atom or central metal ion. So the central metal atom or central metal ion is represented as CMA, central metal atom or ion. Now, this first point we learned, the central metal atom or ion produces or furnishes or creates definite number of vacant orbitals. The second point is the number of vacant orbitals. The number of vacant orbitals corresponds to its coordination number. What is the second point? The number of vacant orbital corresponds to its what? Coordination number. Meaning, what is the coordination number of copper here? How many monodentate ligands we have? How many monodentate ligands we have? What is the coordination number of copper? Please tell me.
Sir, 4.
Oh, 4. Coordination number is 4.
Four,
When the coordination number is 4, it means copper should create 4 vacant orbitals. If I write a molecule like this, K4FeCN6, if I write this complex, the central metal atom or ion here is iron, CMA. Now the ligand is cyanide. What's the coordination number of iron? What is the coordination number of iron?
Sir, is it -4?
No, coordination number
Sir,
cannot be
six,
-4. How many monodentate ligands we have?
So 6.
Sir,
6. I am
So
see
6,
coordination. Yeah, 6. Coordination number stands for the number of monodentate ligands. So it is 6 ligands. We learned in so many examples I gave you. So coordination number here is 6. That means iron has to create how many vacant orbitals? 6 vacant orbitals. Here copper has to create how many vacant orbitals? 4 vacant orbitals. Are you following? So that is what it says. Now the first point we learned, the central metal atom or ion, it should produce or create definite number of vacant orbitals. What is that definite number? How much is that definite number? That definite number depends on the coordination number. The coordination number of copper here is 4. So therefore, copper should create 4 vacant orbitals. Iron, the coordination number is 6. Therefore, iron has to create 6 vacant orbitals. All right. So next is oh my God. The next point is these vacant orbitals should undergo hybridization. So creating same number of vacant orbitals. The third point is the vacant orbitals undergoes hybridization to form same number of hybrid orbitals. Same number of what orbitals? Hybrid orbital. What is hybridization? Mixing of atomic orbitals or overlapping of atomic orbitals to form same number of hybrid orbital is called as hybridization. See, the structure of the complex, the fourth point is important. The structure of the complex, depends on hybridization. So what do you mean by that? The complex structure depends on hybridization. If the complex undergoes sp hybridization, that is one s orbital and one p orbital, if they undergo hybridization, they will lead to the formation of two sp hybrid orbital. Whenever the hybridization is sp, then the structure of the complex is linear. If one s orbital and two p orbital, if they involve in hybridization, totally 3 orbitals are involved. So therefore 3 hybrid orbitals will be formed. The name of that hybrid orbital is sp2. Whenever the hybridization is sp2, they will have triangular planar structure. Now if the hybridization is s and 3p, the totally 4 atomic orbitals are there. Therefore, 4 hybrid orbitals will be formed. What is the name of hybrid orbital? sp3. Whenever the sp3 hybridization takes place, the shape of the molecule will be tetrahedral. when one d orbital, one s orbital, and two p orbital involves in hybridization, totally 4 atomic orbitals. So the name of that atomic orbitals will be dsp2, 1d, 1s, and 2p. Therefore, dsp2. So whenever the hybridization is dsp2, the structure will be square planar. The structure will be square planar. If the molecule undergoes 1s and 3p and d2, 2d. If 1s, 3p, and 2d, they undergo hybridization, it forms totally 6 atomic orbitals are there. Therefore, 6sp3d2. The structure will be octahedral. Octahedral. If 2d, 3p, and d2 sp3, 1s and this is 1s and 3p. Totally again, the same thing I'm writing. So the hybridization will be 6 d2 sp3. d2 sp3. This also will be octahedral. Octahedral. What is the difference between sp3 d2 and d2 sp3? We're going to learn now. The next point we're going to learn. The first 4 points in valence bond theory, are you clear with? What is the first point? The central metal atom or the ion generates definite number of vacant orbital. The second point is the definite number of vacant orbital corresponds to its coordination number. It corresponds to its coordination number. Third point, these vacant orbitals will undergo hybridization to form hybrid orbitals. The fourth point is the structure of the complex depends on the hybridization. Now, structure of complex depends on the hybridization. If s orbital and p orbital involves in hybridization, the molecule formed will have linear structure. So if the molecule undergoes sp2 hybridization, they will have triangular planar hybridization, tetrahedral. If it is d2 sp2 hybridization, it's square planar. If sp3 d2, it is octahedral. If it is d2 sp3, it is octahedral. Did you follow so far?
Yes, sir.
You understand these 4 points? You understand these 4 points?
Yes, sir.
Yeah. The fifth and the sixth point we will try to learn now. Now the fifth point I will write here. I will try to write here, fifth point. Now, if n-1 d orbital involve in hybridization, then the complex is inner complex. It is called as inner complex. What do you mean by that? We will learn. The same point, if nd orbital involves, nd orbitals involves in hybridization, it forms outer complex. It forms what complex? Outer complex. What do you mean by outer complex and inner complex? Now just observe here. Now when we write the electronic configuration, we write it as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 10. Then it comes what 4p, 6 and 4d, 10. It goes on like this. This is the electronic configuration. Now coming to n-1 d orbital. Now if I represent the atomic number as only restrict with the 3d10, all right, which is the outermost orbit? 4. 4 minus 1 is 3. If outermost orbit is 4, s electrons are 4 or 4th orbit, and d electrons are from 3 orbit, then we call it as n-1 d orbital. So the outermost orbit is 4, but inner d electrons are taking part in hybridization. So those are called as n-1 d orbital. 4 minus 1 is what? 3. So those d orbitals, if they involve in hybridization, it leads to the formation of something called as inner complex. Now, when I say nd orbital, now instead of the restriction here, if I say 4d orbitals is taking part in the hybridization, outermost orbit is what? 4. And in that, the 4d electrons is involved in hybridization. So n is the outermost orbit. So if 4d is taking part, the outermost d electrons, then it is called as outer complex. Then it is called as what? Outer complex. Did you understand the difference between n-1 and nd? Followed what this means?
Yes, sir. Yes, sir.
Yeah. Now you tell me Hund's rule of maximum multiplicity. Anybody? Hund's rule of maximum multiplicity. What is Hund's rule? You have learned it in first PUC school also you have learned. Tell me what is Hund's rule of maximum multiplicity. Electron gets paired only when all the available orbital has one electron. Only then what happens? Electrons get paired in an orbital. For an example, if I write oxygen, atomic number 2s2 and 2p4. If we take p subshell, it has 3 orbitals. I cannot write like this. I cannot write like this. Why? Because px, py, and pz have same energy. Since they have same energy, what all the available orbitals should have 1 electron each. Only then the 4th electron gets paired. This is called as what rule? It is called as Hund's rule of maximum multiplicity. It's called as what? Hund's rule of maximum multiplicity. All right. Now, the last point what we're going to learn here is there are different types of ligands. When we say different types of ligands, the 6th point, strong ligand we have, weak ligand we have. When strong ligand approach the central metal atom or ion, strong ligand, then example is ammonia and cyanide. Ammonia and cyanide approach the central metal ion or the atom. Pairing of electron takes place in the atom. That means it goes against what rule? Hund's rule. It goes against Hund's rule. See, pairing of electron within the atom takes place. So Hund's rule says all the available orbitals should have 1 electron, only then pairing takes place. But whenever a strong ligand approach the central metal atom or ion, like cyanide or ammonia, then pairing of electron within the metal ion takes place. Therefore, it goes against what rule? Hund's rule. All right. Did you follow this? 6 points. Is it clear?
Yes, sir.
The first point is, we are going to learn the structures quickly now. The central metal atom or ion produces or furnishes definite number of vacant orbitals. How many number of vacant orbitals it produces? It depends on the number of coordination number. It depends on the coordination number. All right. The third point is these vacant orbital which was produced, they undergo hybridization to form same number of hybrid orbitals. The fourth point is the structure of the complex depends on the hybridization. The structure of the complex depends on hybridization. I've given you the different hybridization part. SP, it will be linear. SP2, it is triangular planar. SP3, it is tetrahedral. DSP2, it is square planar. SP3, D2, it is octahedral. And D2, SP3, it is again octahedral. The fifth point is if n-1d electron takes place or it involves in hybridization, it forms inner complex. When nd electrons involve in hybridization, it forms outer complex. When a strong ligand approaches the central metal ion or atom, pairing of electron takes place. So strong ligand, remember, cyanide and ammonia is a strong ligand for your level. There are so many other strong ligands. We will learn about that a little later. So pairing of electron takes place within the central metal. It goes against what rule? Hund's rule. These are the postulates of valence bond theory. See, you can see here, what are the postulates of valence bond theory? Here also we are learning. Now the first point is suitable number of atomic orbitals of the central metal ion hybridized to provide empty orbitals. The same statement I told you. The first 2 points they didn't mention. So clearly they are mentioning here suitable number of atomic orbitals. They undergo hybridization to form hybrid orbitals. These hybrid orbitals accept lone pair of electrons from the ligand and are directed towards the ligand position according to the geometry of the complex. This is a wrong postulate. Don't worry about this. That's why I didn't give you this point. No, the lone pair of electrons are given by the ligands and they are accepted by the hybrid orbitals. True, but type of bonding is not mentioned here. And the next is N-1D are used in hybridization. They call as inner complex or hyperligated complex or spin complex. So if ND electrons or orbitals are involved, it's called as outer complex. A substance which does not contain any unpaired electron is not attracted by the magnet. It is called as diamagnetic. When a molecule contains no unpaired electrons, then it is diamagnetic. All right. When a molecule contains unpaired electrons, they will be attracted by the magnetic field and they are called as paramagnetic. Magnetic properties also we have to suggest and we have to learn. So magnetic moment is calculated by the formula. Spin magnetic moment is spin only magnetic moment is calculated by the formula square root of n into n plus 2. This is in D block elements you would have learned, but anyways, here also we will try to introduce. N stands for number of unpaired electron. N stands for number of unpaired electrons. So the unit for magnetic moment is Bohr magneton. Bohr magneton, it's represented as capital B and M. So magnetic moment is given by the formula square root of n into n plus 2. What is this n into n plus 2? N stands for number of unpaired electrons. So the unit for magnetic moment is Bohr magneton. All right, see here, there's another point here. There are two types of ligands, namely strong field ligand and weak field ligand. Strong field ligands capable of forcing the electron of the metal ion to pair up if required. I told you it goes against what rule? Hund's rule. So strong field ligand will force the electrons to pair up in the metal atom. It goes against Hund's rule. Pairing is done only to the extent which is required to cause hybridization possible. See, example for strong field ligands. I told cyanide and ammonia. There is carbon monoxide, ethylene diamine, water, nitrate ion, pyridine. They all are strong field ligands. Halogens generally. Halogens are weak field ligands, I minus, Br minus, Cl minus, F minus, nitrate ion, hydroxy ion, oxalato ion, ammonia, they have mentioned it wrong here. And they are all, they can be included in strong and weak. That's what it means. I will teach you the spectrochemical series, then we will understand. All right. So halogens is weak field ligand. You remember halogens is weak field ligand. So what are the limitations of valence bond theory? Valence bond theory was fairly successful in explaining qualitative and the geometry and magnetic behavior of the complex, but could not explain the following. The origin of their absorption spectra could not be explained. The origin of absorption spectra could not be explained. Why did the different complexes of same metal show different colors? Why the different complexes of the same metal show different colors was not explained. All right, meaning, what does it mean? Now, if I take CO, NH3, 6 times 3 plus, and if I take CO, F6, 3 minus. See, the metal is same here. Ligands are different. Since ligands are different, they show different colors. And this valence bond theory was not able to explain relative stabilities of different complexes. So failed to explain the stabilities of different complexes. And why should certain ligand form high spin while others form low spin complexes? The theory did not explain. These are the limitations or drawbacks of valence bond theory. All right. Followed with this? So far?
Yes, sir.
Now just go through these postulates again so that we can write the structures now. I'm just asking you to go through these postulates. Quickly go through these postulates. We'll come back and we'll learn the structures. I'll bring the notebook. Have you gone through the postulates? Yeah? Students, yes?
One second.
Yes, sir.
Yes, sir, done, sir.
Now I'll erase this so that we can do the structures. Now, because I will ask you, when we are going to learn the structures, I'll ask you these postulates. You should be in a position to interact with me. That is why. Right.
Yes.
Yeah, 1 minute. Just give me some time. One minute, man. Just have patience. Now we're going to learn the structures of complexes based on valence bond theory, the postulates of valence bond theory. Right. So the first question is explain the structure of hexaamine cobalt 3 ion. Explain the structure of hexaamine cobalt 3 ion. What is the structure of hexaamine cobalt 3 ion based on valence bond theory? Firstly, can anyone tell me what will be the structure of this? Can anyone tell me what will be the structure of this hexaamine cobalt ion? You can try. Hexa means how many?
So octahedral.
No. I'm asking you the molecular formula. I'm not asking you the structure. What's the formula of this? Hexa means how much? 6. Hexaamine means 6 ammonia molecule. And you have cobalt. Central metal atom is cobalt. And the charge on this cobalt is 3+. Therefore, it is called as hexaamine cobalt 3+ ions. This is 3+, not minus 3+. You do understand? You should be in a position to write the structure of the complexes also based on the nomenclature. All right. So we'll do one in detail. I'll take a little time to explain this. The other examples will go a little faster. All right. Now, first point is, from the name of the complex ion or from the molecular representation, what is the central metal atom or ion? What is the central metal atom or ion? It is cobalt. Cobalt is the metal, right? Is cobalt the metal, yes or no?
Yes, sir.
Yes. The second point is, what is the atomic number of cobalt? What is the atomic number of cobalt? Atomic number of cobalt is 27. The third point is, what is the electronic configuration? EC stands for electronic configuration. It is argon configuration 4s2 and 3d7. 4s2, 3d7. 4s2, 3d7. Now tell me, what is the charge on cobalt here? As a whole, the charge is +3. Ammonia is a neutral molecule. 0 into 6 is 0. Cobalt, we take it as X. So X will be equal to what now? +3. The charge on cobalt is +3. That is the fourth point. Oxidation number of cobalt is +3. Oxidation number of cobalt is +3. When we say oxidation number of cobalt is +3, what does it mean? +3 electrons are lost. From where the +3 electrons will be lost? 2 electrons from 4s and 1 electron from 3d. So when 3 electrons are lost, what will be the electronic configuration of cobalt 3+? What will be the electronic configuration of cobalt 3+? It will have argon configuration and 3d6. Did you follow this?
Yes, sir.
Yeah. All right, good. The sixth point is, what is the coordination number of cobalt? What is the coordination number of cobalt?
So 6.
Yeah. What are the first postulates in the valence bond theory? The central metal atom or ion should create definite number of vacant orbital. The second point is, the definite number of vacant orbital corresponds to its coordination number. Now the coordination number of cobalt is 6. It means cobalt has to create how many vacant orbitals? How many vacant orbitals?
Sir, 6.
6 vacant orbitals. Now when I say 6 vacant orbitals, now if I write the electronic configuration of cobalt 3 plus, what will be the electronic configuration of cobalt 3 plus? The electronic configuration of cobalt 3 plus is d subshell has 5 orbitals. D subshell has 5 orbitals. We have 6 electrons. 1, 2, 3, 4, 5, and 6. This is 3d. Now the next higher orbital is 4s. Initially we had 4s also. After 4s, the higher orbital possible is 4p. Higher orbital possible is 4p. So vacant orbitals cannot be created from the inner atomic orbitals. It should be from the outer atomic orbitals. Did you follow this? Did you follow the electronic configuration? This vacant orbitals also. Yes or no?
Yes, sir.
Yeah. Now you tell me, ammonia is what type of ligand? When ammonia, whether it's a strong ligand or weak ligand?
Strong ligand.
When ammonia strong ligand approach the central metal atom, what should take place? Pairing of electrons within the central metal takes place. What do you mean by that? So pairing of electrons within the central metal takes place. What does it mean? This electron gets paired here. This electron gets paired here. So this two becomes what now? Empty? Yes or no?
Yes, sir.
All right. Takes place creating, see what I'm writing, creating two 3d orbitals, one 4s orbital, and three 4p orbitals vacant. How will you write this representation? You will write the representation like this. This is d orbital. 1, 2, 3, 4, 5, and 6. See, d orbital is vacant now. And 4s is vacant and 4p is also vacant. Did you follow this?
Yes,
Yes, sir.
Did you follow?
Yes, sir.
Yes, sir.
Involves in hybridization. Involves in hybridization to form 6 D2sp3 hybrid orbitals. Now, how do you represent the D2sp3 hybrid orbitals? How many now? 6, 1, 2, 3, 4, 5, and 6. These are called as what? D2sp3. How do I write that? Now you can see 3 D2, 1 4s, and what? 3 4p. They involve in hybridization to form 6 D2sp3 hybrid orbitals. Followed? Students, are you following?
Yes, sir.
Yes, sir.
Now, these hybrid orbitals, these 6 D2sp3 hybrid orbitals accepts 6 pairs of electrons from 6 ammonia molecules. 6 ammonia molecules to form 6 coordinate bond. So what is that I've written? 6 dsp2 hybrid orbitals accept 6 pairs of electron from ammonia molecule to form 6 coordinate bond. How do I represent that? I represent this like this: 1, 2, 3, 4, 5, and 6. See, to differentiate, what we do is we write different colors here. These are electrons donated by the ligands. These are donated by the ligands. These are donated by the ligands. Now tell me, any unpaired electrons are there? Since there's no unpaired
No, sir.
electrons, yeah, it will be diamagnetic. The complex will be diamagnetic. I'll draw the structure here. Firstly, I'll erase this. All right, the complex is diamagnetic. Complex is diamagnetic. Why? No unpaired electrons. And what will be the structure? Structure will be octahedral. When we say structure is octahedral, you should write cobalt here, 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 ammonia molecules, 6 ammonia molecules. You will write 6 ammonia molecules like this. Here also ammonia, and here also ammonia, and you will have this. So what will be the charge on this? This is the structure, is 3 plus. This is the structure of the molecule. Just go through this. Students, go through this. I hope that you followed.
Yes, sir.
Yeah. Just go through. We will learn the other example now. Ajay,
Yes, sir.
yeah, did you understand this?
Yes, sir. Understood, sir.
Yeah, we'll do one more. Quickly, we will do one more, and then we'll stop for today because I'm not giving well. That is hexafluorido. Hexafluorido cobalt. Hexafluorido cobalt. Now, firstly, before we go for that, what type of complex is this? What type of electrons? 4s is there and 3d. 3d electrons involved in hybridization. Therefore, it will be called as inner complex. Inner complex. Now, hexafluorido. Cobaltate. Cobaltate ion. So it will be COF6 3 minus. It's an anionic complex. It's an anionic complex. Now we'll have to understand this. I'll modify this. That's all. All right. This I'll remove. Till here, this will be same. See, the central metal ion is cobalt. Right, atomic number of cobalt is same, electronic configuration is same, oxidation number of this is also same, +3, coordination number of cobalt is same. This is the electronic configuration of cobalt, it's fine. Now coming to the ligand here, this ligand is a weak ligand. Fluoride is a weak ligand. When fluoride ion is a weak ligand, no pairing of electron takes place. What do you mean by that? These electrons will not get paired up. When they don't get paired up, what is the next possibility? Next possibility is this 4d. Because we need 6 electrons, 6 vacant orbitals totally, because coordination number is 6. So 1 is from S, 3 is from P, and next is 4d. The outermost orbit is 4d. No pairing of electron takes place within the central metal, creating what? 1 4s, 3 4p, and what? 2 4d orbitals vacant, creating 4, what's that? Understood or not what I'm telling? Understood or not?
Yes, sir. Understood, sir.
Creating two 4D vacant orbitals. So how will I represent that? I'll represent this like this is 3D. 3D. We have 1, 2, 3, 4, 5, and 6. This is 3D. The next higher orbital is 4s, vacant. Next higher orbital is 4p. And next is what? 4d. So totally 6. 1, 2, 3, 4, 5, 6. Now these vacant orbitals will undergo hybridization to form what? What will be the name of this hybrid orbital? Name of this hybrid orbital will be what? 6 sp3d2, because the first orbit is here what? S. So this will undergo hybridization to form 6 sp3d2 hybrid orbital. sp3d2. Since it forms 6 sp3d2 hybrid orbital, sp3d2, this hybrid orbital accepts 6 pairs of electrons donated from 6 fluoride ions to form 6 coordinate bond. This also remains the same. The structure, this will be diamagnetic or paramagnetic? It will be diamagnetic or paramagnetic? You can see here we have unpaired electrons. Therefore, it will be what? Paramagnetic.
So paramagnetic.
Yeah. And what will be the structure of ammonia? You will have what? Fluoride ion. You will have fluoride ion. This is F. 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 And this is F. 3 minus. So it forms an outer complex. Why it forms an outer complex? Because 4 electrons, 4D electrons are involved in hybridization. Therefore, it forms an outer complex. Did you follow this?
Yes, sir.
Lakshmi, you followed. Ajay, you followed. Just go through.
Yes, sir. Follow.
Yes, sir. Follow, sir.
Lakshmi, did you follow?
Yes, sir. Follow.
Madam, I'll stop the class, ma'am. I'm finding a little difficult with my health. Kindly help me. I'll continue possibly tomorrow. Ma'am.
Okay, sir.